All right, so chemical formula. I want to say in this brief video that chemical formula is more than just calculating molecular weight or ratio of atoms in a compound. You know, there are hydrocarbons, alkane, alkene, alkynes. And you also have corresponding cyclic structures of alkane, alkene, and alkyne. And let's try to understand the formula. Let's first put the general formula for alkane and alkyne. So alkane's general formula is a Cn, H2n plus 2. Say you have butane, then you find 4 carbons, and each carbon has 2 hydrogens. So you can say when you have an n number of carbon, you should have a 2n number of hydrogen, but wait, you have 2 missing hydrogen, 1 here, 1 there for terminal carbons, so plus 2 more. That's why it became Cn H2n plus 2 for alkane. Then what is the general formula for alkene? Well, in order to form double bond, you need to remove 2 hydrogens, right? Then you can create 1 double bond. So you can say Cn H2n for alkene. However, alkene doesn't mean that you have 1 double bond. You could have diene, triene, tetraene. So whenever you see 1 pi bond, you know you lost 2 hydrogens. For diene, then you should have Cn H2n after losing 2 hydrogens from the alkane. But you lost 1 more pair of hydrogen to form second double bond, so minus 2. If you have 1 more double bond, then you should lose 2 more hydrogens. So that is not actually general formula for alkene. That's the formula for alkene with 1 double bond. So I made it up one formula, something like this. This is alkane. Whenever you have a double bond, you lose 2. So 1 double bond, 2 double bond, 3 double bonds. Then you know how many hydrogens you lose from the hydrogens you have from the alkane. So N is number of carbon, X is number of double bond for alkene. But you don't need to memorize the formula. You can come up with the concept. Then you know the alkyne has a triple bond that contains 2 pi bonds. So we talked about it here. So the general formula for the case you have 1 triple bond, it's 2n minus 2 after losing 1, and then 1 more pair from here. So 2 pair of hydrogens are lost. So this is the general formula for alkyne when you have only 1. But without making formula like this, you can come up with the idea how many triple bond you have if you have a certain number of hydrogen. If you know every triple bond need 4 hydrogen loss. All right. For the cyclic structures, let's go with the cycloalkane. If you have a cyclopropane, for example, like this, you have 3 carbons, and this is alkane, all single bond, no pi bond. However, if you count number of hydrogen, there are only 6. So if this is alkane, this should be the general formula, but it's not the case. If you plug in 3 here, there, then 2 times 3, 6 plus 2, 8. But there are only 6 hydrogens. So what happened? Well, when you form a cyclic ring, 2 hydrogens on each, and you had 2 more, but to form a ring, you need to lose 1 and 2 hydrogens. Then you need to connect these 2 carbons. So you know, the cyclic structure need to lose 2 hydrogen from the chain structure of corresponding hydrocarbons. So for cycloalkane, you need 2 less from the alkane. So you get the formula like this. Then you know, for cycloalkene with a 1 double bond, then you need to lose 2 more from the alkene, so 2n -2. Then for alkyne with a 1 triple bond, you need to lose 4 from here and 2 more from there, also 2 more from the chain form of the alkyne in order to form a ring. So general formula to have 1 triple bond in a cyclic structure is this. But again, if you form 1 more, you know, ring, like you have a bicyclic structure, something like this, right? You have 2 rings here. If you count this alkane, bicycloalkane, the formula is carbon 2, 4, 6, 7, and the hydrogens are 2, 4, 6, 8, 10, 11, 12. So if you come up with the general formula, it's almost like CnH. Then 2 times 7 is 14, right? But it's only 12, so -2. But it's alkane. Alkane cyclostructure should be CnH2n, but it's a CnH2n minus 2 because you made 1 more ring. So whenever you form ring, like we talked about before, you need to lose 2 more hydrogen whenever you form additional ring. So please don't get confused with the statement on the question that when they say alkene, they don't necessarily mean the alkene with a 1 double bond. Also, when they say cycloalkane, they don't mean the cyclohexane type of 1 ring alkane. It could be multi-ring structures. Okay, so when you have oxygen in the formula, what happens to the number of hydrogens? Say you have a Z number of oxygen. Well, you cannot also memorize the formula easily, so let's go with the understanding of the structure. Say you have 4 carbons. There you have 3 hydrogens here, right? But when you insert 1 oxygen, for example, you know that's not complete, so you have to put that hydrogen back on. So what happened to the number of hydrogen when you put oxygen in the structure? You didn't change any. Without oxygen, there should be 3. With oxygen, still 3 hydrogens. Even when you insert oxygen in the middle of the carbon with the 4 carbons, what happened to the number of hydrogen? Well, you had 3, 2, 2, 3. So 10. How many do you have after having additional oxygen? 3, 2, 2, 3, so 10. No change. When you put 1 more oxygen, 2 more oxygen, it doesn't change. So if this was a alkane with whatever number of oxygen in it, the formula should be same as the normal alkane, so 2n plus 2. Even for the alkene, same. Alkyne, same. and the cycloalkane, cycloalkene, cycloalkyne, the formula do not change from the original formula for each type of hydrocarbons. Okay, what if you have X number of nitrogen in the formula? What happens to the number of hydrogen? So let's try this trick again. If you have 3 carbons, for example, and I want to insert nitrogen, then in order to complete the octet rule here, you need to add 2 more hydrogens. But how many did you have originally without nitrogen on this carbon? Just 1 more, right? You have still this hydrogen, so just 1 more. Meaning, in order to accommodate 1 nitrogen, you need original hydrogen, but 1 more hydrogen. So additional hydrogen you need. If you want to add here where you find 3 hydrogens and accommodate another nitrogen, you keep that hydrogen from this carbon, but you need 1 more. So whenever you add nitrogen to the structure, you know you need additional hydrogen. Therefore, if you have X number of nitrogen, you need X more number of hydrogen. So the number of hydrogen for alkane, straight chain alkane, you need 2N plus 2 plus X number of hydrogen. So what if you have alkene? Say, we cannot do all of them, right? So let's try cycloalkene with the 2 double bonds. So how do you come up with the formula? With 2 nitrogens in it. So when you have, say, 6 carbon and you have 2 double bonds, so to be alkane you need to have 2 times 6 plus 2. Then to have 2 double bonds you need to lose 2 each, so 4 hydrogens. Then in order to have 2 more nitrogens, each nitrogen adds 1 more hydrogen. So there are 2 nitrogen, so 2 more. Therefore, you have total here 12 and 14, then 10, then 12. So total of 12 hydrogens. So the formula to have 2 double bonds and 2 nitrogen of, did I consider the ring structure? I didn't, right? So let's see, alkane, 2 double bonds, 2 nitrogen, and to be cycloalkene, and say this has only 1 ring, then you need to lose 2 more hydrogen. Therefore it's not 12, it's 10 hydrogens you need. So the formula should be C6H10 and 2. So let's try to draw it. With a 6 carbon, there are many possible isomers you need to practice, but let's say you have a cyclohexane. So I made up the cyclo structure, but it's alkene. I said there are 2 double bonds. So let's just put 1 double bond. It could be here, here, but let's put it here, 2 double bonds. Then I had 2 nitrogens, randomly making up nitrogen here and here. Very symmetric molecule we just came up with. Let's see how many carbons and hydrogens and nitrogens we have, and that fits in this formula. Okay, so there are 2, 4, 6 carbons, yes, and it should be 10 hydrogen. 2, 4, 5, 6, 7, 8, 9, 10, and 2 nitrogen. So see, that indeed works. So these ways of thinking will allow you to apply this and think of the situation like this. You have n number of carbon and you have 2 chlorine, then how many hydrogen you need for straight chain alkyne? Okay, and there's only one, let's just say only one triple bond, not diene, but just one ine. So for alkane you need 2n plus 2. Then to be alkyne with one alkyne, you need to lose 4 hydrogen to form 2 pi bonds. What about, what's the cost to have 2 chlorines? And if you think about it, when you have 4 hydrogens and you like to have a chlorine here, you cannot simply have a chlorine with a hydrogen. If you have a chlorine, you cannot have a hydrogen, so you are losing hydrogen whenever you have chlorine. And you have 2 chlorines, so you need to lose 2 hydrogens. So that's the number of hydrogens you should have, which is 2n negative 4. So you can think of all kinds of combinations, and you should be able to calculate how many triple bond or double bond or rings you may have. So let's really practice with a formula given and see you can figure them out. Okay, what do you think of this formula? If this was alkane with a 10 carbon, the hydrogen number should be 2 times 10 plus 2, which is 22. You only have 14, meaning you lost 8 hydrogen atoms. So with the 8 hydrogen lost, what can you think of? This is almost like you are having 4 H2 gases you lost. But you know, whenever you lose 2 hydrogens, you can form 1 pi bond or 1 ring. So my golden rule, I have to tell you here, whenever you see 4 or greater, then you have to think about having a benzene ring. How many loss of H2 you need to form this from 6 carbon? 6 carbon alkane without ring structure is 2,4,6 hexane, right? So from here to there, how many H2s you need to lose? To form 3 double bonds, you need 2 there, 2 there, 2 there. So you lost 6 already. 3 H2s you lost to make this out of the alkane form. Now you have a triene. To cyclize them, you need to lose 1 more. So you have 1 hydrogen, but 2 and 2. So you need to lose 1 from here, 1 from there to have this ring. As you can see here, 1 hydrogen, not 2 and the 2. So additional 2 hydrogen you lose. Then finally you lose 4 H2, which is 8 hydrogen. So this is very much like a stable ring in nature. So it is a good assumption. Whenever you have 4, you may have a ring there. What if you lost the 10 hydrogen from some formula? Then you may have, like the case 4 lost to form a ring, and you may have lost 2 more. Then this 2 more can be what? Can you think of the case? It could be either you have 1 additional double bond, or you could have 1 more ring there. So this 10 carbon compound use 6 carbon to form a benzene ring, and then other 4 carbons form no ring, no double bond, so they must be a straight chain. So you can guess it could be 4 more carbon like a straight chain, or it could be 3 more sorry, 3 more carbons here, 1 more carbon here or here or here. You can think of other isomer, but at least you know you have a benzene ring. Okay, what about this case? If this was alkane again, you can say 7 carbon with a 1 nitrogen. You should have, if it's alkane, 2 times 7 plus 2, then whenever you have a nitrogen, you add 1 more hydrogen. So you have 1 nitrogen, so 1 more hydrogen. Altogether, for alkane, you should have a 14 plus 3, so 17. However, you have the real molecule given, only 9 hydrogen on it. So you again lost 8 hydrogen. So you lost 4 H2s. So again, it's the case you have a benzene ring. But you need to check. How do you check this? Well, you can use IR NMR. Okay? So whenever you lose a certain number of hydrogen, we can call this degree of unsaturation. Okay? Unsaturation means either pi bond as a double or triple bond, or the ring structure. Basically, unsaturation means you lost the hydrogen, so they are not alkane chain. Even the alkane cyclic structure is considered unsaturated. Alkynes are obviously unsaturated. So degree of unsaturation tells you how many double bond, pi bond, or ring structure you may have. So here you have a degree of unsaturation 4. Sometimes they call it as an index of hydrogen deficiency, and they are exactly same concept. Okay, what do you think of this? If you have 5 and like to be saturated compound, so we assume first saturated, the compound is saturated, so we can tell how many degree of unsaturation we have. So hydrogen with a 1 oxygen, but you know about oxygen. Oxygen do not change number of hydrogen, so you can ignore that in the calculation. So 5 times 2 plus 2 should be the alkane number of hydrogen. Here you have 12 and you have a 12. So this compound, you don't have double bond or ring or triple bond, okay? So let's start looking at the IR spectrum and the connect. This will help you to simplify and the problem solving, and we'll see that. So when you look at this structure, this spectrum with the formula here, C5H12O, you can see OH, not carboxylic acid. So it's regular OH, alcohol OH, and 3000 is right here. So it looks like there's no CH over 3000, so everything should be sp3. And here there's nothing, and you might want to say, oh, this could be this is around 22, close to 22, so maybe sp, but there is no hydrogen here. So if this is considered a triple bond, then this triple bond in the middle of the chain, you might want to say, and you're not clear about it. And 14, 15, and this peak is a little over 1450. So is it CC double bond or not? This is not awful situation, but there are times the data can be even more confusing. But if you know this C5H12O, like we practiced, This formula is telling us that it is alkane with the OH. 5 times 2 plus 2 is 12. There's no double bond, there's no ring. It must be straight chain. It may have a branch, but it must be straight chain. The information about straight or branched, we cannot tell by an IR easily, so we will go to the NMR for more clear thinking. So at least we know this is not real peak, and that's not even CC double bond. And that's thanks to the formula analysis. Okay, here. How about this? You have this peak. It could be CH of SP, but it's quite intense, but you've seen similar things before. CH of SP hybridized carbon can be this intense, but also this can be NH, not NH2, but NH. Not as broad, so that's a confusing part. Also, if you look at the 28, 29, 3000, over 3000 you have a couple peaks as well. So we're not sure whether that's a CH from the sp2 or sp, or even from the aromatic ring. We're not clear. Also here 14, 15, 16, we have 1600 peak and 1500 and 1450 some, and this is quite intense. So there must be some polarity, right? But whether these two peaks indicates aromatic ring or one double bond or two double bonds, that's not clear. We know this is a CC double bond region, but that's not clear. But when you have formula, we know, oh, we have a nitrogen. So that kind of clarify this must be NH, not NH2. So it could be, it is a strong evidence, I think, it is NH. But we still don't know. So there are some question marks here, here, here. So we need to look into the formula. See how important the formula becomes. So if you analyze this, 2 times 8, 16, plus 2, 18. Then you have a 1 nitrogen, so it should be 19. So for saturated compound, you need 19 hydrogen, you have 11 hydrogen, so you are missing 8 hydrogens, meaning 4 hydrogen molecule, meaning you have a degree of unsaturation of 4. So, like I said, if the degree of unsaturation is 4, you may have a benzene ring. Say if you happen to have a degree of unsaturation 5, like I mentioned, then you have benzene ring. Then benzene ring takes up 4 degree of unsaturation. Then you have a 1 degree of unsaturation left. Then you can use that to thinking of 1 additional double bond or 1 additional ring. Okay? But in this case, you have only 4 degree of unsaturation. And you can justify these are all benzene ring CH stretchings of sp2 carbon, and these are from aromatic rings. You have 1, 2, maybe 3, 4, relatively strong. That means out of 8 carbon, you used it for benzene, 6 of them. There are 2 more carbon, and there's 1 nitrogen. But we know the nitrogen is directly attached to the ring, so the nitrogen can have a resonance with the ring, so it can intensify the signal of the benzene ring. Without nitrogen conjugated with the ring, these normally are smaller. So this is what I mean. You have benzene ring, you use the 6 carbons, and the degree of unsaturation 4 is used here, 1, 2, 3, and the ring makes fourth degree of unsaturation. So you use the all. Then you have one nitrogen left, two more carbons left, and you have some hydrogens. And how do you put them together? And I'm trying to say that the two carbons are not here to have a nitrogen. It's not even NH2, right? NH there. It must be the case that nitrogen is right on the benzene ring. So due to the resonance, even inductive, the nitrogen makes the ring signals very intense. Then what else can you do? Well, you know the nitrogen is NH. So you have one hydrogen there. Then you cannot have another hydrogen because then it should be NH2, meaning you have at least one carbon attached there. So that much is clear from IR, okay? So because of the formula analysis, we can go this far. Then you have one more carbon to attach, because you have two carbons left. As you can see, I'm not taking care of a hydrogen yet, okay? So the one left over carbon cannot be here, so it should be there or anywhere else, which we don't know. And obviously, if you know a little more of IR, you can go to the region of 800 to 600. There's a particular pattern for the intense signal for bending vibration of the ring that can tell you about whether it's a mono substituted or bi substituted. And for the bi-substituted, whether it's ortho, mera, or para isomer, we can actually deduce, but we're not gonna do that, okay? So it will be acceptable for a sophomore organic chemist student. You can have another carbon here. Then you can add hydrogens to make them a stable structure, such as this. And then we assume that there are one hydrogen each on 4 carbons. So whenever I attach methyl group on any carbon, you mean you are taking off hydrogen, then you put the carbon instead, right? For example, I'm trying to move this carbon over here, meaning I'm gonna take it off and put it here. What really means now you have to be careful that way. Taking off the methyl off of this carbon, putting it here means you have one hydrogen now. You didn't have any hydrogen, right? So at the moment you take it off, you have to fill in with the hydrogen. And in order to put methyl group there, you have to take off hydrogen. So basically you took up the hydrogen from here and put it there in order to shift the methyl group from here to there. So that's why I'm not taking care of the hydrogen during the puzzle fitting, but I do that in the last. But you always have to be aware of the number of hydrogen that's not visible. That's why your foundation of Lewis structure, line angle drawing, and those are important. So let's see it makes sense. You have, and then you have 4, 3 more 7, 8, 3 more 11 hydrogens and 1 nitrogens, and you got one of the possible isomers, and there are more isomers that fit into the IR spectrum you've seen before. In order to distinguish those isomers that's possible, you need a more accurate NMR data or other data. Okay, this should be our last practice, but what do you see here? Okay, so when you analyze the formula, as you can see here, you have the saturated alkane with 1 oxygen. That doesn't change the number of hydrogen, right? Oxygen doesn't. So the formula should have a 14 hydrogen, but it has 10 hydrogen. If you subtract it, then you have a 4 hydrogen atom missing, meaning you have a degree of unsaturation 2. So it's not 4, so you don't have aromatic ring. Then what are the cases you can think of to have a 2 degree of unsaturation? Remember, each degree of unsaturation can be 1 pi bond or 1 ring structure. So when you have a 2 degree of unsaturation, you can think of a triple bond. So do you have a triple bond? Where do you go for a triple bond? 2200, which is around here, is very clean, right? So there's nothing, no triple bond. And it could be 2 double bonds, or 1 double bond and a ring, or 2 rings. But for double bonds, okay, case number 2 and the 3, you can have a double bonds, but double bond with the oxygen in the formula, you can think of 2 types of double bond. It could be CO double bond or CC double bond. So, removing case 1, the triple bond, from the possible choices, you need to clarify what types of double bond, or whether you have double bond or not. For the case, you might have 2 rings. So go back to the IR and see. So the double bond region is 2000 to 1000 from here to there, and you see some peaks, luckily. And then you see this peak around 1700, and that's a 1718. If you remember, 1718 is a regular carbonyl group. So you have a CO double bond. So at least you have a 1 double bond. So it could be not 4, right? You rejected. Number 1 was already rejected. So it could be one of these 2 cases, but we know one of the double bond is already CO double bond. So let's figure out other 2. As you can see, with the formula analysis, your interpretation of the spectrum, the approach is just somewhat different. You're not blindly reading all the possible signals, okay? That could lead you to the confusion. So I would highly recommend you go with the analysis of the formula when you read the spectrum. If you naively just go to the spectrum and match the frequency to assign the signals, then you may get lost. So you look for the other double bond. You have only 1 oxygen, so it cannot be another CO double bond. So you may have a C double bond, not triple bond, okay? No ring, maybe. We don't know yet. So where do you find the hint for the carbon-carbon double bond, since we don't have a carbon-oxygen double bond? 2 places. You go for the sp2CH stretchings over 3000. So let's check. 3000, and you have 1. Good news. Then you need to confirm by going to the double bond area, right? Around 1600 and below. So 1600 something, you have sharp peak, and that cannot be bending vibration, so it must be CC double bond. So you have CC double bond. So indeed you have second case right here. Okay, second case. So no more ring, no more double bond. That's it. And you have a 6 carbons. So earlier, if you only based on just the spectrum, you can come up with a lot of variations of isomers. But now we know you have 6 carbon, and that carbonyl is not aldehyde, because there's no signal at 2750, which is right here. So it is a ketone. So you gotta have a ketone. So minimum 3 carbons, because it has to be ketone. It cannot be hydrogen here or here. So you have CH3 and something here. So then you have to have a double bond. But double bond, it's not one of the variation case. The CC double bond is not conjugated with a CO double bond. We know that because the carbonyl is at normal typical number. And the double bond is not intensified. The alkene is like a normal, small, sharp signal as the typical double bond alkene would do. That means over here, you cannot put double bond here. You gotta have this carbon left as at least 1 carbon, right? As the alkane, then you can have double bond here. Then how many carbons you have used? 1, 2, 3, 4, 5. So from this information, you can add 1 more carbon, either here or here. And those are the 2 possible isomers you can think of. Like that, okay? Well, there are more isomers you can think of. That 1 additional carbon can go over here as well. Sorry, this is not there. Like this one. Or you can think of this one. Even you can think of the cis form of this double bond area. So you can come up with several answers using the key backbone we figured, avoiding conjugation and having typical ketone, carbon here, carbon there. That's great. And also you can think of the case, the conjugation is avoided by having 2 carbons, right? Then this is it. You have 1, 2, 3, 4, 5, 6 carbons. And that's the only way you can have. So there's one possibility. And those are a couple possibilities using this backbone. Have a 6th carbon. Out of the 6 carbon, we found 5, right? So 6th carbon can come here, there, and there, and you can think of the cis form of that. Those are the only isomers you can think. So we narrow it down very much logically. Then from here, you can go to NMR, and then you can easily narrow it down. So if you develop the logical thinking this way, when you get into the other spectrum, you can logically connect them well. You cannot ever blindly just label certain signals and hope to put them together like a jigsaw puzzle and somehow you get the right structure. That's almost like you are a blinded person touching gigantic animal and try to figure out what that is. It's very difficult activity that way. So hopefully the fact that the formula is not just for molecular weight calculation and showing us the ratio of the type of atoms, but it could be very informative. And then this video served the purpose, and I'll see you next time.